Okay, let's continue. What we're going to do next is we're going to do an example to show how the unit impulse response can be calculated. And we'll go through the procedure. So let's do the example that we use here. So we'll copy that example down. Let's see, where is it? Okay. So it's right here. So we're going to use the example that you're seeing on the screen. So we have a second order system. And we're trying to find the unit impulse response of this linear time invariant system. So if you want to follow the procedure, okay, meaning we want to use this equation directly, or this if you want to do this, we need to answer a few questions before obtaining the answer. First of all, what is Bn? Secondly, what is P of D? And then, what is Yn of T? Now, the first two questions can be directly obtained without any calculation. Just by inspecting the original differential equation, we know well Bn should be equal to 0 since there's no second order derivative term on the right hand side of this equation because there's no d2f dt squared term. So this implies that B2 has to be 0, and since n equal to 2 in this particular example, that means this Bn term is going to be 0. Second, PD we discussed in class is actually the polynomial of D on the right hand side. So in this case, you have df dt, that will be the D term. And then you have this 4f, so that's actually constant 4. Okay, so this is PD. And then for this y of n signal, what we need to do is, well, we need to keep in mind that this guy is also a sum of the exponential signals, where the exponential signal comes from the roots of the characteristic equation. The characteristic equation that we have found earlier look like this, which gives us the two roots, lambda 1 lambda 2, equal to -1 and -2. So for this Yn of t, we have b1e negative t plus b2e negative 2t. And then it follows immediately that we need to figure out what is b1, what is b2. And the value of the two constants should be calculated based on that special set of initial condition particularly made for the unit impulse response. So what we're going to do is, well, since the second order system, we need two equations. The first equation, or the first initial condition, will be Yn of 0 is going to be this particular expression evaluated at t equal to 0, so that will give me b1 plus b2, since e to the power 0 is actually equal to 1. And the special initial condition asks all the equations to be equal to 0 except for the last one. So for this particular case, we need two equations to solve two constants. Now we have the first one. The second one actually will be the last one, which will be constructed by taking the first derivative and evaluate it at t equal to 0. So when we do this, we take the derivative on the first term, that will give me negative b1, evaluate it at t equal to 0, so e to the 0 will still be 1. And for the second term will be negative 2, b2, again evaluate it, and should be e to the power negative 2t here, but since we want t equal to 0, this will make the entire thing go to 1. As a result, we can simply erase this term completely from the equation since it's equal to 1. And for this initial condition, since this is the last equation we need to solve the b coefficients, we'll set it to 1. Okay. So now you have two equations, you have two unknowns. You can just take a few minutes to solve this, which won't be difficult. So for this one, we'll be able to figure out what b1 should actually be equal to 1. And b2 should be equal to negative 1. So if you plug these two values into these two equations, you'll find them to be right. So go back to yn of t. You'll be able to write it down. So e negative t minus e negative 2t. Now remember, although you have obtained y of sub n of t, so you got this guy figured out, keep in mind you need to do one more thing. Don't make a common mistake that we'll let's put in red here. Make sure you need to do one more thing. You need to take this p of t and apply it to this yn of t that you just obtained. So we're going to do it like this. So h of t should be equal to b n times delta. We figure out this b is equal to 0. So for the first term, this guy won't appear in the solution, and we can directly go to the second term. So this will be written as 0 times delta t plus, we'll need to apply this d plus 4 to this yn, which will be e negative t minus e negative 2t u of t. That means, well, for the first term, we don't have to write it down anymore. For the second term, we need to take the derivative of e negative t minus e negative 2t. And we need to take plus 4 e negative t minus e negative 2t. And this entire thing will be multiplied by u of t. Okay. So what we just did is we take d, that's a derivative or differentiation operation, to the equation following it, and then so this will result in this particular term. Then we take the second 4, multiply it with this equation again, and obtain the second term. Okay. And the last step will just be some mechanical work. You need to take the derivative, physically take the derivative. So for the first one, we have negative e negative t, and then this minus becomes plus 2e negative 2t, and then still plus 4 e negative t minus e negative 2t as we have it before. And this thing will be multiplied by u of t. And finally, you can combine the terms. You have a negative e negative t and 4 e negative t, so that will give you 3 e to the negative t. And then you have 2 e to the negative 2t, you have minus 4 e to the negative 2t, so altogether will give you minus 2 e negative 2t times u of t. Okay, and that's it. Now, This will be a typical procedure to solve for a unit impulse response. It takes several steps. First of all, you need to figure out what is Bn. You need to figure out what is PD. You need to find the characteristic equation, solve the roots, and write down the expression, general expression for this Yn signal, and then use the special designed set of initial condition, this one and this one, to solve the undetermined coefficients B1 and B2. And while you obtain your Yn signal or Y sub n function, don't rush to the final answer yet, because you need to take one more step, which is outlined right here. And some algebraic manipulation will lead to the final results as we have seen at the very end. Okay, so this is the typical step we will see. Now, a quick observation when we look at the impulse response. Remember, the impulse response h of t is obtained assuming what? Assuming the input to the system is a special one, is actually an impulse spike that takes place at time t. Okay. Always keeps in mind that when we talk about h of t, when we talk about impulse response, it always implies that you already know what the input signal is, okay, your delta function. This is very important. We're going to use this particular assumption, sort of a hidden assumption in the number of cases. So keep this in mind. Now, although this input signal delta t only appears at a singular time instant, and you will have nothing before this time instant, and input basic will disappear after t equals 0. Although it only appears at one singular point, through this particular example we'll see, well, it actually generates the response of the system in terms of two exponential signals. Okay. That will actually be going on starting from t equal to 0 to t equal to infinity. Okay. If you plot this out, you will see the actual thing. And another observation is, look at these two signals, e to the negative t, e to the negative 2t. You also have both of these terms when we try to solve the zero input response. See this particular example right here. We have also this negative t term and e to the negative 2t term. This implies that these exponential terms are actually very special. Since they're so special, in general we have e to the lambda 1t, e to the lambda 2t, and if we have an nth order system, we have to e to the lambda nt. All of these are called the modes of the LTI system. Because it defines the internal property, how the system will behave internally, regardless the response are caused by just the initial condition, or the response is caused by a short, strong flick. You always see these terms. You always see these terms, all this e to the power lambdas. Now, towards the end of this chapter, we will discuss, well, since they are so important, and since all the exponential signals are defined by these lambdas, by the roots of the characteristic equation, maybe some of the properties of the system can be derived by directly looking at the values of these lambdas. And we'll discuss this later on in this chapter. Okay.